Hello everyone, my name is James Pruitt. This is my second lecture on JavaScript, and as I said, we're going to implement a computer algebra system using JavaScript. And our first step along that way, the foundation of our computer algebra system, is going to be a large integer type. So that's what we're doing now. So let's talk about how we're going to represent that large integer. We're going to do it the basic way, nothing fancy. So we're going to have to represent our large integer as an array, as standard as we always do, as an array of numbers. For instance, we have a number A3, A2, A1, A0. These are all four numbers, and they're put in order. So this is the 0th place, the first place, the 2's place, the 3's place, the 3rd place. So this is an array of numbers, and this is how we're going to represent that number. And the actual number is, we can compute the actual number by taking, given a base, we're given a base or a radix. B is the radix or base. A3 times B cubed plus A2 times B squared plus A1 times B1 plus A0 times B0. Okay, so that's our number, where the A sub i's are all greater than 0, less than B. This is a standard way to represent a number, and we're going to follow that way. And so our number is going to be represented by an array where the place determines what this implicit multiplication. So this implies, this A third implies this multiplication by B cubed. This position in this array, this A2's position in the array, determines what you multiply it by. And each of the AI's are going to be greater than equal to 0 or less than the base. And B is called the base or radix. And right now that's what we want to determine, how big the base or radix is. And we want to have it as big as possible within our JavaScript constraints. JavaScript's only number type is a double, so that's what constrains us. So we want to keep the base within that. So we're going to look at what JavaScript, talk about the JavaScript number type in order to determine what our base is for our number system. And then once we determine our base, our number system is just going to be an array of numbers where the place in the array determines what the multiplication of the power of the base. Okay, so JavaScript number type, JavaScript's number type allows consecutive integers. I don't think I'm saying this properly. Consecutive integers from -2 to the 53rd power to 2 to the 53. These are the bounds, and we talked about this last time. Once you go beyond those bounds, you can actually, the double can go up to 2 to the 10 to the 23, right? Once you go past that, you're going to start getting skipping a lot of integers, right? Because and the principle is, if I'm worried about the distance between celestial bodies, I don't care what a few hundred miles are. That's meaningless to me when you're talking about light years. So as far as physics and physical applications, it's all right to drop off those integers, but we can't do it in a computer algebra system. We have to be able to we have to grow our integer type so we don't lose any accuracy at all. So our bounds, we're constrained within that bounds because the IEEE 754 number type only has 53 bits of significant figures. So once we go past that 53, we start skipping integers. So that's our boundary. So what does that say? That says that our base, the base has to be, and our base is going to be a positive number. Our base has to be less than or equal to 2 to the 53, right? And what we also want, we also have to take into effect that we have to use the primitive operations that JavaScript gives us on their number type. So we can't make up our own operation. We have to use their multiplication, their addition, their JavaScript's multiplication, JavaScript's division, JavaScript's addition, subtraction, modulus. We have to use that to build up our multiplication, our addition, etc. So if we're going to take two numbers, we're going to multiply two numbers in using JavaScript multiplication, we're going to get b squared. If I multiply b by b, I get b squared, and I still want that b squared. If that goes above 2 to the 53, it's going to cut off. It's going to cut off integers, and we're going to lose accuracy. So we need that to be less than or equal to 2 to the 53. Because if not, when we start doing our multiplication is going to cause us to lose accuracy. So we have to, that's a further restriction. So if we take the square root of both sides, 1/2 less than or equal to 2 to the 53 to the 1/2, that's going to be equal to b, has to be less than or equal to 2 to the 26.5. And here, I program assembly language, and I like, when I have a radix or a number system, I like it to be a power of 2, because that way when I divide by a power of 2, I'm just shifting. And I don't know if that's important, and I just have a gut feeling that for me, I want to set b equal to 2 to the 26 instead of 2 to the 26.5. I don't want to have, I wanted the radix to be a power of 2. That it just get in my gut, that just feels right. And I don't know if I can make a better argument, and I don't want to take too much time because I'm only going to lose one bit. If I worked really hard, I could get that bit, but if I do it this way, I'm only losing one bit of information. So I'm going to do it this way. So we determined that our radix is going to be 2 to the 26, and we can see that we're still, the largest number we can represent in our number system now, that our radix b is equal to 2 to the 26, is 2 to the 26 minus 1. That's the biggest number we can represent. If we multiply that by 2 to the 26 minus 1, we get 2 to the 52 minus, okay, you got negative 2 to the 26 minus negative 2 to the 26, that's minus 2 times 2 to the 26 is 2 to the 27 plus 1. And that's definitely less than 2 to the 53. So we're good to go. So we can multiply in our system and we won't lose any integers. We're safe. So now we've determined our radix of our number system. Now we can start start implementing our thinking about how we're going to implement that. And one of the design criterions I have on my let's see what time we have set on. Okay, we're setting pretty good. One of the design criterions I want to do is we're going to have an array, right? We're going to have an array of numbers. Each of those numbers are going to be less than 2 to the 26. An array of numbers. We're going to implement our numbers using we're going to implement large integer with an array of numbers, all of which are less than 2 to the 26. And so we're going to have an array like of numbers A0, A1, A2, A3, like we described before. So A3 would be multiplied by 2 to the 26, that cubed. So these are, its position in the array implies the multiplication by the base to the certain power. So what I want to do is I just don't want to have an array floating by itself out there. So if I grab it, I might accidentally manipulate it and cause it to knock it off or do something with that array. It can be easily manipulated and changed. I want my numbers to be fixed. Once I constructed that number, I want it to be a constant that no one can touch. So we're going to do that. Let's see, 47 times. So we're going to do that. We have to look at how JavaScript will allow us to implement a constant. And so I'm studying now. Talk a little about programming. The book that I've read that I've heard that many people say it's the best introduction to computer science is Structure and Interpretation of Computer Programs. And that's online, and if you go Google that, you can go to their website and you can read the book for yourself. And they also have some videos at MIT OpenCourseWare. The authors of the book have 20 videos. But anyway, the authors say the main thing, the most important thing they say is when you're studying a language, what are the primitives? Of the language? What are means of combination? And what are the means of abstraction? And a JavaScript implements lambda calculus, and so you have the lambda calculus view of abstractions or forming forming abstractions, and they also have object-oriented programming through prototypes, a prototype-based object-oriented programming. I want to deal for what I want to do with this number. I'm going to try using this this means of abstraction based on lambda calculus called closures. Okay, let's push this up here. And closures is a way it has to do with free and bound variables of your functions, and we'll talk about it next time. The authors of the book, Structure and Interpretation of Computer Programs, didn't like the term closures, but it's so common now, I'm going to use it. They prefer closure to mean something else, and I'll talk about that too. Anyway, we'll stop right here, and I'm going to talk about closures next time and about abstractions and how we're going to use those closures to implement our large integer type, to make those that array a constant. Okay, talk to you in a second.